Okay, good evening everybody. I hope everyone's having a wonderful day. First, before we get too far ahead of things, I just want to remind you of where we were last day, because it's been a little while. So last day I was trying to put together these big pieces of concepts that we've seen, things like input size, algorithms, and problems. I had to go a little faster over the concept of an algorithm. Now, believe it or not, because of the courses you may have taken previously, you already have sort of some familiarity or intuition around algorithms already. For example, when you write a computer program, it follows a sequential step-by-step process. You give the instructions to the computer to execute them. This is an example of an algorithm. So there's one thing in this definition I really wanted to kind of emphasize first before I get too ahead of myself, is this notion of unambiguous. Now, you may or may not know what that word means. It's not very much, it's not a technical term. It's just a descriptor for what I'm describing here. So just recall, an algorithm is, at least for us, this is our, keep in mind, we can always go deeper than this definition. So we're working at this depth of what this concept means. In a course that you may take in the future, you may learn a much more exact definition for an algorithm. So it's an unambiguous step-by-step procedure that takes an instance or the input for that instance as inputs and produces output for the problem instance. So there's kind of two things I want to point out. First, this unambiguous aspect here. So we already talked about the step-by-step, but you're familiar with this idea because we've written some computer programs in the past, right? So this unambiguous part, this is normally how I like to explain it to people, is that the algorithm needs to be sufficiently described. It needs to be described well enough so that you can communicate to somebody that they can't misinterpret what you're trying to tell them, okay? So just as an example, I'll tell you a little bit of a story. So just as an example, sometimes on my journeys, I sometimes run into like signs on the side of the road. And there's this one that I always went by, and it looks something like this. It wasn't exactly this, but it was quite similar to this. And it had a phone number. It says Combat Animal Care, and it had a phone number on it. So if you've seen this sign, you might say, okay, so what is this sign trying to tell me? So is it that it's a business that's called Combat Animal Care? Or is it telling me that I'm supposed to combat animal care? Which is it? It's a little unclear, right? This is what I mean by ambiguity. This sign looks ambiguous to somebody that doesn't understand that that's a name of a place that you can go for animal care. It's just that they called it Combat Animal Care as opposed to being about combating animal care. Yes, let's be nice to our little friends, okay? But the point I'm getting at is that in this course, very often when I introduce an algorithm to you, I'll usually describe it often either in words, or I'll often describe it using something I call pseudocode, or what people might call pseudocode. So very often these will get described to you. It might get described, say, for example, in English, or they might be described in what we call pseudocode. Pseudocode is this, it doesn't have any one convention, but very commonly follows many of the control structures and rules that you're familiar with from a programming language. But it's not specific to any one programming language. So for example, this is a nice substitute for example, when we talk about, say, C++ code, very often people say, okay, so how do I do it in C++? Somebody might ask, okay, well, how do I do it in Java? Or how do I do it in Python? So what pseudocode is for is about describing the algorithm. So I'm going to give you an example of this very shortly. And it's not about describing it in any one programming language. It's meant to be so that you can communicate exactly what you mean. Just like when, for example, I give you a program that does, say, implements, say, an algorithm like bubble sort over there. If I have a function that communicates bubble sort in C++, I can also write a method, for example, in Java that also describes bubble sort. I can also write one up in Python, for example. The point is that if you look at the code itself, there's actually, the description of the algorithm doesn't change. It's just that it's the syntax and the rules of the programming language that change. So what we would like to do is describe the algorithms to you so that I don't have to get very specific about programming languages, and I can communicate just what the algorithm is to you. So is that clear, everybody? So you'll find in this course, I'll very often use word descriptions and pseudocode to describe algorithms. And then what happens is once you have one of these written in a way that it's clearly communicated to you, so there's no way you can wiggle around with how it's interpreted, then what you can do is you can pick that up and implement it in your favorite programming language. So one thing I want to touch upon that I said last day, just to kind of add on to this, is that whenever we look at this algorithm concept, remember, it's problem-centric. It's all about problems in the way I've defined an algorithm for you. So it produces output, and we say that output's correct if it is a solution to the problem instance. And ideally, what I would like to do, so first, just I see somebody mentioning about the video. Are you hearing me perfectly fine, or is it just that there's some delay in the video? Just want to clarify. Or is it fine for everybody? Just want to make sure. So it's fine? Okay. I just wanted to make sure. Okay, wonderful, wonderful. I just want to double check, everybody. Just keep in mind, if there's any technical issues, the lecture will be available after class, okay? But I do appreciate this, because earlier today I actually had some glitch out happen in my lecture where my streaming software froze on me and basically no one could hear me. It was really funky. But anyways, let's get back to this. So ideally, when we want to have an algorithm that solves a problem, it should be that for every problem instance, that when I give it instance to my algorithm, it has to produce correct output. So we have examples of these. You've seen examples before. I'm just going to bring up some of them. So for example, you may have seen some examples of sorting algorithms in your past studies. You may or may not have. Either way, here's some examples of sorting algorithms that solve the sorting problem. So all of these, if I were to give you an array of so-called comparable elements, these are just simply elements that I can list from. There's a way I can compare them so I know which element can come before or after. If you want to just think about it in terms of numbers, I can have it so I can compare which number is smaller than another number, or I can tell you that they're the same number. So these are examples of comparable elements. All of these algorithms will work for any array where I give you n elements and I want to sort them so that they're listed from smallest to largest. So I could give it any one array of length n. Any one of these will sort the array. So that shouldn't be anything wild or anything, right? So if I were to say, hypothetically speaking, just me being hypothetical with you, if say, for example, bubble sort, if I gave it one array and it didn't sort it properly, just from last time, would you say that that algorithm is correct or incorrect? If say there's one instance that I give to the algorithm and it doesn't actually do what I asked it to. Yeah, it's incorrect, right? Exactly. So we have to be careful about that. That's why we're going to talk a little bit today about correctness. So an algorithm is correct if for every instance of the problem, it always produces correct output. So that's what we're going to use as our definition for a correct algorithm. So it means it solves the problem. So there's two common ways or two common criteria to this. So these are the two that we'll focus on. So when I want to establish this, two things you can do is you could show that the algorithm terminates in finite time. And the other is that the algorithm produces correct output. right? Because it couldn't possibly output anything if it doesn't terminate in finite time, right? It has to terminate to output correct answer to you, right? So these are two common criteria for correctness. So very often when you're coming across an algorithm and you want to know, is it going to solve my problem? These are two common conditions to establish the correctness of an algorithm. So are we okay with these two conditions? So these are two very common conditions that people tend to establish for showing that an algorithm is correct and thus solves a problem. I must stress that often when you come across so-called proofs of correctness or a proof of correctness, sometimes they even bury this first condition into the second one because often it might be really straightforward. Other times it's useful to prove the first one and then come off to the second one. We'll see an example of that today. So anyways, that being said, why don't we proceed on over here? Let's go over here. So I want to talk about a problem that I know you're familiar with. We talked a little bit about this. So we talked briefly, well, we talked a bit about the search problem before. So in the search problem, remember that I'm given an array and I'm going to assume for our purposes of this discussion that it's n integers that are going to be in my set S. And I'm going to be representing this set S as an array, and I'm going to call that L. So each one of the instances for my problem is going to be an array of numbers. And I'm also going to be giving it a key that I would like to search for. X may be in L, or X may not be in L. So if it's in L, I would like to know where it is. If it's not an L, I would like it to return -1, just to tell me, oh yeah, it doesn't exist in the array. That's going to just be a simple setup for us right here. So just to do an example, just to illustrate this idea. Actually, before I do that, I have a question for you. What would be a reasonable way of characterizing the input size for this problem? Any suggestions? So far, I'm seeing some pretty interesting and good suggestions. So I see n. N is a very good suggestion. In fact, this would be the one I would recommend you use because I'm given an array with n elements in it and just some integer. But the integer this doesn't grow or shrink with the array, right? It's just another element. I could have just wrote n+1 over there and it wouldn't have made any difference. But really, I want to focus on just how many elements and how those might scale. So this is just the number of elements I have here. And notice I have 10 of them in this case. But when you talk about input size, that delicate detail doesn't really matter a whole lot. But in this case, for this instance, I'm given 10 elements in my array. So suppose, just for our purposes, just to explain this, just so everybody's on the same footing with this, suppose I asked and I said, okay, so suppose I gave you x being 22. So what should be the a solution for this? So if I give you this array and I give you the key being 22, what should be a solution for this? So remember, our goal is to identify where it exists, if it exists, in the array. Otherwise, we return -1. Yeah, element 5, everybody's getting this, wonderful. So see, it's right here. It's right there. So if I give you 22, what I would like is it to as an answer, I want it to tell me the position. In this case, it's position 5 in the array. Okay, so suppose instead of being 22, suppose x instead, so in this case, you find it right here. If x is 8, what should I return if I wanted to design an algorithm to solve this? Yeah, I'm seeing it. Wonderful, wonderful. I'm just seeing absolutely the chat just getting drowned in -1s. This is very good. And yeah, it isn't here. Perfect. Yeah, it's not in L. So in this case, we better return -1, right? Meaning it's it's not in L, right? Wonderful. So I have a question. I'm pretty sure we talked about this, but I feel the need to kind of stress this. Could somebody describe to me how I could identify what we just did here? So can somebody describe, or at least tell me the name of an algorithm that I could use to do this? Yeah, perfect. Yeah, linear search. Exactly. So I could describe linear search to you. So for example, I'm just going to say that linear search can be used to solve this problem, right? That's at least what we would like to say, right? Yes, just to clarify, somebody's asking about the solution for this case where I give you L and X is the key. And if it was 8, yes, the answer would be -1. Yes. Yes, so that would be what it returns. Yes, exactly. So you might say, okay, Dan, you said that often you'll describe algorithms in words or as the so-called pseudocode, this strange thing. Now, you could, for example, describe linear search in words, which I do in the notes. Now, for the purposes of time for us, I'm going to ask you to take a look in the notes after class. So I give a brief English summary. An English description in the notes. So I encourage you to just take a look at that, just to get a flavor for how you could describe an algorithm without talking about source code. So that's the first thing. So I think everybody's got the general flavor for this, is that we're talking about linear search. And now, naturally, I need to have some way of describing this to you. So let's talk about that. So I must stress again that when we talk about pseudocode, and I must stress the reason why I'm showing you linear search now is really to illustrate this concept to you. Is pseudocode, remember, its job is to describe an algorithm. It's not, so often when people write out algorithms, they typically will give a little summary of what it is in words, and then they might write down some pseudocode if it seems to be relevant. So here's an example. You'll find I'll very often follow these conventions in this course just to keep it simple, and I also like to keep it consistent for you. So that way you could kind of pick up your own way of writing out an algorithm. So I'm going to usually just say algorithm, and then I'll describe what it is. And you'll see that I'm going to use notations very similar to how you would write out the signature of a function, for example. So here are my parameters or inputs for the array. Now, just for my sake, I felt like just including the length of the array n in here. Yes, the notes are updated after each class. Correct. So remember, because we're trying to solve a problem, I have to tell you what the inputs and outputs are for my algorithm, because that's ultimately a key part. So notice the way I defined a problem also naturally fits into this like a glove. So my input is going to be an array L of size n, and the value, and I get a value or key x, and I would like it to output a position I such that L sub I, so this is just some array-based index, is equal to x if x is in L, and -1 if x is not in L. So notice I've clearly defined what the input is and the output is for the algorithm. So this is a very important part because it's actually characterizing what your algorithm's trying to accomplish. So whenever you describe one of these, it's just like when you document code, for example. I want to make sure I clearly specify what my inputs and outputs are. But remember, in the context here, we're talking about an algorithm that solves the search problem. So let me describe how we could write this. This is one of many ways, by the way, of writing linear search. You're going to find that this is rather useful for us to write it like this. So I'm going to first write down a first instruction here. Now, you might look at this and say, okay, well, what the heck is that? You might say, okay, so in a lot of programming languages, when you see the equal sign, this equal sign, what is that in a programming language? What is that? It's assignment, perfect. So in a programming language, this is assignment. So when I'm going to write out my pseudocode, just because it makes it a little easier for me to write things out, I'm going to often use a left arrow to mean assignment. So this is one thing I'll point out. Another thing, and in fact, this is actually something that is done also in other programming languages sometimes. Some programming languages even use this syntax, is sometimes they use a colon, then an equal sign. Sometimes they write define as to mean a colon with an equal sign. So both of these are pretty commonly used in pseudocode for assignment. So you'll find that I'll often we use this left arrow just to keep things simple. Because remember, if we're writing out an algorithm, we have to be very clear with our audience, right? So if I mean equals, like equal to, well, what is that? Well, I would have to write out two equal signs probably if I want to keep my programming-like syntax. But it might be much easier for me to just write out another symbol for assignment, which is what it actually is, as opposed to using an equal sign when I actually mean equals. Does everybody get the idea? So we're going to talk about assignment. Now next, you might ask, okay, well, how can I write out a control structure? Because you know I'm going to need a loop here. So here's an idea. What I could do is I can write out a while loop, and I could use the same kind of structure you're familiar with from a programming language. You could do the same thing with for loops. You'll see lots and lots of examples of this in this course, by the way. So if I have a while loop, I want to make sure that it scans all the way from, it goes from the left of the array, it goes from the left all the way to the right, starting right at the left. So I start in position 0. I would like it to go all the way up to position n-1, but if it goes one further, you don't access the array, right? We don't want that to happen. And 2, we've explored all the elements if it doesn't exist, right? So what I'm going to do is I'm going to take advantage of a feature that many programming languages have. It's you may have heard of this. It's called short-circuiting. This feature is going to be, let me just write down this and I'll explain it. Sometimes it's rather useful, but there's a very easy way of rewriting this pseudocode so you don't have to do this at all. I'll explain in one moment. So here's the condition of my while loop, and I'm going to make it so it increases this value I by 1 wherever I don't actually find a match yet. So while I is less than n, and L sub I is not equal to x, we're going to increase I by 1. Now, I mentioned about this short-circuiting. Now, has anybody never heard of short-circuiting before? It's okay if you haven't. I could easily explain it for you. Okay, so very often in some programming languages, if you have it where you have multiple conditions in say for example, a conditional statement, like an if statement, you can take advantage of, in many programming languages, a concept called short-circuiting. What it does is you evaluate the conditions as they appear from left to right. If any one of them becomes false, if they're all connected by AND operators, that means that it will not evaluate the rest of the statement. So in some languages, you can actually facilitate this explicitly using the logical AND operator. You may know it as, you may have seen it like like this. Exactly, exactly. So that's what I mean by short circuiting. Yeah, the 2 ampersands. So that's what I mean when I write and here. So this is just to ensure that when I becomes n, it does not check this condition. Okay? But if you don't like this, I'm happy to take another way of writing this. You could have easily just wrote while I is less than n, then put that into an if statement inside. Would it be improper to write? Nope, that's perfectly fine. If you want to write I++, that's cool. As long as it's clear to the reader, it's okay. So if you're never unsure about like what you're communicating to them, you can always just mention it off to the side. You could say, this means I'm incrementing I by 1. That's it. So now I have my while loop. Now I need to make this so that it does something very natural for us. Now, and you might ask, Dan, why are you writing it this way? You could have wrote it this other way by using, say, a return statement inside the loop, which is absolutely fine. So this is just an explicit, this is just a style thing. Some languages, they'll actually have an explicit do command. So you may or may not have heard of while, like do while loops versus while do loops. It's a little bit strange, but this is just a matter of me just saying, while this, do blank. That's all I'm doing here. If you don't like that, you can easily just not write that, and you can just put, like, say, curly braces around here. It's not mandatory, no. This is just me trying to give you a flavor for how you could write pseudocode. Like I said, there's not one universal standard for pseudocode. You try to find a way of communicating it clearly to your reader, okay? So now, if you think back to linear search, the idea here is I would like to access each position of L sub I until I get a match, right? But I might not ever find that match. So the whole idea here is I'm going to keep increasing this until this condition fails, right? Or this condition will fail. So after my while loop, now if I'm not sure about where things are indented, so here I'm using indenting just to be very clear. So after my while loop, I can check if I is equal to n, then we can return. So a question for you, if I is equal to n, at the end of this loop, what should I return? Yes, -1. -1. That means that we went through all of the elements. Perfect. You guys are pros at this. Wonderful. Otherwise, so I'm going to have an if-else here. And if I have this, otherwise, I'm just going to return the position I'm at. So I just return I. So if I showed you this, you'd be like, okay, this is linear search. You'd say, yeah, that describes what I know to be linear search. You may describe it in a different way, slightly differently. For example, you could, write a for loop where it goes through all of the elements, and then maybe when it gets a match, it returns that position. Question. Does our pseudocode have to be in this exact style? No, it does not. No. It can be a bit different. So for example, just to give you an idea, like I mentioned, if you don't want to write these do's here, you just put curly braces, or you make use of indenting. You're welcome to do these types of things, just like when you're writing up a computer program. Some people like to put their curly braces on the same line as their conditions. Some people like to put them on the line afterwards. It's quite similar to that. Yes, you can write it in your own way, as long as it's clear to the reader, okay? So if ever there's something that's really unclear to somebody, you just make sure you explicitly state it, okay? Yes, so somebody's asking, will we have questions about writing pseudocode? Yes, and you will try to do this on the first assignment. That's why we're having this discussion. So I want to make sure you have an opportunity to try doing this. And we're going to see lots of examples of this in this course. So don't worry, this isn't the only time I'm going to show you pseudocode. You're going to see a lot of that in this course. But yeah, no, it's a very convenient way of describing an algorithm to somebody without having to say, like, one confide it to given programming constructions of a given language. But also, it's just a matter of describing it in a way that's natural for example, those familiar with programming. So here's my assignments, here's a loop, here's an if statement, there's an else. But I find that this is a rather simple way of following through. But you're going to see more examples, so don't worry. This isn't like the only one you'll see. So, yes, so L sub I is not equal to X, yes. Okay, so what we're doing here, so remember, just to make sure I remind you. So remember, linear search, what we do is we start at position 0 in the array. So that's what I's purpose is just to allow us to access each successive position. From left to right, we're going to sweep the array. So what we do is we just sweep the array, we check if this is X. So for example, if X was say right here. Notice that whatever's here isn't X. So what happens is I increase I by 1. Now I is 1. I check if it's X. Well, it's not equal to X, and I is less than N, so we're going to increase I by 1. So then I make it 2. And then I check, okay, that's not X, so I increase it I by 1. Now I'm at 3, and I check this, and I say, hey, look, L sub I is in fact, it is equal to X. So you know this condition is falsified. It means it's false here, meaning that you will not execute any further this loop. It's meant to stop us when we get a match. Yes, exactly. So somebody's asking, can we do this with a for loop? Yes, exactly. So so actually, I'll be giving an example in the notes within the next lecture or so with some loops. So you can see how you could write out a loop. But yeah, linear search, like you could have easily just replaced this with a for loop. Like I mentioned earlier, you can make it so it goes through a loop just like what you would expect. And you can have it where you have an if statement inside where you just check if L sub I is equal to X. And you can make it return I right there if you wanted to, and just have it where it returns -1 at the end of the loop when it's finished completing. Well, certainly you could do that. But now, this is one thing I want to bring up. This is rather important for our discussion here today. Okay, notice that I would like to argue that linear search is actually correct, meaning that there is no way you can feed an instance to this problem where it's going to make a mistake. Now, this all comes down to presentation of one's algorithm. And sometimes you might say, Dan, why would you show it this way as opposed to, because you think about it more practically speaking, you could have indeed wrote a for loop right here. You can have an if statement checking if L sub I is equal to X and return I as early as possible. Here, I keep it going all the way until the end, right? I don't even break out of the loop until I get that match, right? But my point is that we could have written this a little differently, but keep in mind this while loop is doing something very similar to that. It's just I chose not to write it like that, which is, you might ask, Dan, why would you do that? You'll see. So the whole point here, and this is one thing I want to point out to you, is that when you come up with an algorithm, you have to keep in mind the way you describe the algorithm to somebody actually can help you establish key properties for it. So for example, notice that if I could establish that while loop always gets exited out at some point, you know either the algorithm is going to return -1 or it's going to return I. Does everybody see that? Notice that I've really just put all the exit points of my algorithm at the bottom. Now, this isn't meant to be something be like, yeah, you have to do it this way. I'm not saying that at all. What I'm saying is that this gives us a lovely property that makes it a little easier for us to establish the correctness of this algorithm. Because if I can justify the first condition for correctness, the one for which I guarantee it terminates in finite time, then I could say right away that the algorithm has to either return -1 or returns I. So does everybody see that? So I see a question. Yes. Yes, what is your question? Yes. So what will so let me walk you through this whole process one more time. So yes. So what will happen is we start off when we assign I to be 0, and then what we do is we're going to check this condition before we enter inside the while loop. So until, there's only two things that can happen here at this stage. So I is going to be either less than n if I'm going in here, or that L sub I is not equal to x. Now, if it becomes the case, so every time both of these are satisfied, I'm going to increase I by 1, which corresponds to me going through each one of these. That's what this one's purpose is. So I've sort of explicitly wrote it there. You could have written an if statement instead. However, when I get this condition being wrong or false, what happens? Well, when I increased I before that, so when I increased I in the previous iteration, I then evaluate this. I is less than n, and L sub I is not equal to x. Now, in this case, L sub I is equal to x. So that means that that becomes false. And because I is less than n, it means it's going to go, okay, so now since that's false, I'm going to stop iterating this while loop. I'm going to check this condition next. Okay, that's not equal to n. So I is not equal to n, so I proceed to this else statement as a default. So yes. Yes, exactly. So notice there's two things that we really have to care about here. One, that this terminates in finite time. So there's either going to be two possibilities that are going to happen, right? Either it's going to hit this one right here, or it's going to be that I gets too big. So if I gets too big, you know you're going to leave this while loop. If you get a match, you leave this loop. And you know either of these, both of these will take some finite number of operations and they will stop. So this will terminate in finite time. But here's the neat part about that, is that if you know it terminates in finite time, that means either one of these two possibilities has to happen. Okay? So does everybody understand our pseudocode for linear search before I proceed? Wonderful. So I want to just make sure you have these couple ideas in your head. Just keep them as a little cap, like a little feather to put into a cap. Because a lot of these ideas are going to pop up in my proof of correctness. Now you might ask, Dan, what is a proof of correctness? So remember, my goal is to establish that for every problem instance, that when I give any one instance to my algorithm, in this case linear search, it produces correct output. Now you might ask, Dan, does this involve that dreaded M word, the mayonnaise? The answer is yes. But most certainly, I must stress that when you get to try doing this for yourself on the first assignment, it's meant to be an opportunity for you to try it. It's not meant to be some sort of thing where I'm going to expect you to be some pro at this. Just to be very clear. So question. So while we do algorithms, we have to focus on these properties. Well, every algorithm will have different properties, but most certainly, yes, if we want to talk about the correctness of the algorithm, we want to make sure that algorithm terminates and it produces correct output. So we're going to often focus on those two things if we really need to get into proving things. So let us show this algorithm is correct. So now you might ask, Dan, how do we do this? We will do so by observing, the end sort of melted there. Let me fix that. So we'll by observing properties of the algorithm. So like what we did earlier. So notice that I pointed out some things to you about what the algorithm does. This is what's going to pop up in our proof, okay? So a lot of the things I just said on the board there would be actually how you could communicate to somebody that linear search actually is correct. I'm just going to write it down. And one thing that I must stress as well is that this algorithm is relatively simple. And a lot of the algorithms we're going to see in this course will be often prone to the types of techniques that we're going to see here. Some won't be. Some will require a little bit more finesse. For those ones that require a little bit more mathematical machinery, we won't most certainly have time to focus on those per se, mostly because I want to make sure that everybody's just getting the general idea as opposed to just being like, yeah, we're doing it for the sake of anything, okay? So sometimes I will establish or prove things for you. Other times it will just be where I'm just going to tell you about a property just because we don't have all the time in the world to do it. Or I feel like maybe it won't really benefit the class, just generally. But I encourage you to check into it or ask me about it. I'll usually give you the idea of the proof, usually verbally in those cases. So I'll say we will do this directly. You might ask, how do you prove something like this directly? Well, okay. So remember, if I establish that this algorithm terminates in finite time, there are exactly two outcomes for that algorithm, right? It either outputs I or it outputs -1, right? It returns one of those two possibilities. So it means that there's always going to be instances where it's going to say, for some of the instances, it's going to spit out -1. Some are going to spit out I. I want to establish that the ones that spit out -1 are the ones where the element doesn't exist. The ones where it returns I want to know that those are where I get the match. Okay? So is that clear, everybody? So that's how I'm able to accomplish this. So you'll find that this is often really helpful, say, for example, when you're trying to come up with an algorithm for problems such as, say, on the first assignment. You'll find this idea very helpful. But if you have more mathematical background, you want to throw something else at it, there's other things as well, such as mathematical induction, but I'm not going to focus on that here. We will do this directly. We'll do this directly, but there are other ways to prove an algorithm is correct. So I'll just say, for example, induction. But we're not going to talk about that here because I don't necessarily know everybody's got that background. And I wouldn't feel right doing that. So anyways, with that being said, let's talk about how we would prove this or write that out. So what I'm going to do for the purposes of time, I'm going to do the first part in its entirety, where we prove that the algorithm terminates in finite time. And then I'm going to give you a sketch of the second part of the proof. But both of them are, I want you to read these carefully. They're both going to be in the notes. And you can take a look at them afterwards. But I just for the purposes of time, I'm just going to sketch the second part of the proof, okay? Otherwise, if we had more time, I would happily do the whole thing here. So hopefully that's understandable. So let's prove the first part in its entirety. So linear search terminates in finite time. So this is the claim that we would like to prove. So this is the claim I would like to prove. So remember, that's property number 1 for correctness for us. So that it terminates in finite time. So here's how I go about it. Now, remember, I must stress, now, I'm not sure of your familiarity with math, these mayonnaise or math, the M word kind of proofs. I'm not sure your familiarity with these. You may have seen some of these, say, for example, in a calculus class. You may have seen some of these there. You're going to find that the way that a lot of these proofs will play out, I will often try to formulate an argument. So what I do is I observe properties of the algorithms, then I try to argue based on those observations for my general conclusion. So one common kind of step away from doing it right is sometimes people look at what I'm doing and they say, oh, you're just explaining the algorithm. Sometimes it will look like that. Just don't confuse an argument with an explanation. They're two different things. So let's walk through this. So I'm just going to reiterate what I said earlier, but I'm going to do it in a more persuasive way. So to prove this claim, observe at the beginning of at the beginning of the algorithm, variable I is set to value 0, right? That's what our linear search we described over there does, right? It starts off by assigning I to be 0. So we're going to find that the way I'm going to argue this is going to be based entirely around I, because I know it starts at 0 and I know it does something based on what its value is. So here we go. 0, and now I'm going to make a comma there. This is a little bit of a long sentence. And after each, so this is my observation I'm making about this loop. After each iteration of the while loop, so what happens after each iteration of the while loop, everybody? What happens to I? It increases by 1. Perfect. Perfect. Yeah, it increases by 1. It's incremented. So let's say that, because that's a very important observation for us. And after each iteration of the while loop, the value of I is increased by 1, right? Now, you might say, Dan, what do we do with this? Well, okay, so if you were to go back to the pseudocode I have over there, you would see that there's an explicit condition that says I has to be less than n, right? So let's just use that, just straight up. We could just use that, because we know that that has to be true along with every other condition in that while loop for it to iterate any further, right? So as long as we know that that condition has to be true, you know that that loop has to keep going, right? So let's just pick on that and let's take it to its next level, okay? So if the while loop performed an infinite number of iterations, then I would be unbounded, right? That means that there is nothing that's really containing what I has to be, right? If I allow this to be an infinite loop. But we know that this thing, it's not unbounded, right? Why is it not unbounded? Why is it not unbounded? Why is it not? So why is it not an infinite loop? Because I has to be less than n. Exactly. So that's all we're going to say here. So you guys are getting this. Awesome. I'm going to put a semicolon. Don't get to use those very often. At least in this setting for now. I like using semicolons, by the way. However, this is not possible as the while loop requires I is less than n, right? So, how do I wind this all up? Now, you could always add a sentence saying that, well, this would have to finish in the worst scenario where I is equal to n, right? Right? I could always add that in a sentence, but for the sake of me running out of space on my board, I'm just going to go right to the conclusion because this is sufficient for what I need to accomplish. Therefore, so note that when I conclude off a proof, I usually write therefore or some other conclusion-based term like hence, thus, or therefore. I advise not using the 3 dots because this is not a symbolic proof. This is a written proof. So this is therefore, let me just fix that F there. Therefore, the algorithm terminates in finite time. I'm sort of running out of space here. But it says, therefore, the algorithm terminates in finite time. And then I end the proof with a box. This is just to illustrate or conclude or cease the proof. So this is just a proof. So notice that I'm making an argument here, but there's a lot of pieces of this we talked about, right? All I'm doing is I'm writing it as an argument. So I start off by observing that about this property about I, and then I say, okay, well, what does that mean when I pull up that while loop? Because that's the thing that determines if it finishes or not, right? And then I just point at that property and say, hey, look, there it is. But I always increases by 1 if that's always satisfied. And we know that I has to be less than n. And boom, there you go. So are there any questions about that? Is this all good? Give me 2 thumbs up if we're okay with this. Wonderful, wonderful. And again, remember, I must stress that I'm not expecting you to be a pro at this, okay? I want you just to try it, okay? So when we try to do this in the course, we're going to be trying this. So a question, what if we more straightforward, wouldn't it be more, what if it would we be, well, generally it's saying, what is there a more straightforward way? What if the value I is unbounded? Yes, you can actually argue right from the get-go that you can observe that this while loop has some condition to it, but you could suppose that if it were to, say, loop forever, that would mean I is unbounded. Then you could just see what happens when that is the case. And you say, okay, well, I'm going to assume for the sake of what we call a contradiction, that I could say, okay, if I is unbounded, then this happens. Then you realize very quickly that, yeah, if I is unbounded, then you're going to assume that I is going to be unbounded while this thing has to terminate at the same time, which leads to what we call in the dreaded M word, the mayonnaise, we would get into a contradiction because to terminate requires this to happen, right? This or that. But the thing is, most certainly, I can't be too big. But yeah, that's another way you can argue this. But most certainly, that's something I like seeing this. I like seeing suggestions about these kind of things. Now, I'm going to give you a sketch for the second part of the proof. I want to explain it in words. But remember, there are 2 possibilities that can happen, right? There's this one and this one. Because, why? Because we know the algorithm terminates in finite time. So when it gets to this point, either this is going to happen where it satisfies this I is equal to n and then it returns -1, or it's going to return I. So so you consider these 2 possibilities. So the easy case is actually this one right here, the second possibility. So if that happens, notice that if that happens, so you know if it returns I, then most certainly you could say, okay, well, it had to have been that I is less than n. Well, what had to become false? This right here. But what does that mean? It means L sub I was equal to x. And that's one part, that's this part right here, checking this condition here. The first part, this is the trickier one. This is the one where all you have to do is really just notice what we did over here, right? So notice it's actually, if you look at my proof that's going to be in the notes, you'll notice that I'm just going to be reiterating a lot of what I just said on the board over there. This is why sometimes you see proofs of correctness where they kind of contract it all into one. So notice that I always goes up by 1 each time. And for this to occur, I had to be equal to n. You can establish that it returns -1 if and only if this means that if this happens, then most certainly the other case has to happen. And if it doesn't happen for the other case, then most certainly it can't happen here. If the algorithm returns -1, this happens always when I is equal to n. But that also means that it's also going to be that you couldn't find it. Why? Because if you look at this, every time I increases by 1, but why does that happen? Because it's not equal to x, and it does this for the first position, the second position, the third position, and so on. But when you think about it, it starts off at 0, and then every time it checks each one of these, right? X is in here, right? So if every time I increase I by 1, each time that's really me saying L sub I is not equal to x. Does everybody see that? Yeah, so about this, so the question about the looping action of this. So the way, at least at this level in this course, I'll just assume because we have this property, because I is always being increased by 1, but this happens every single time both of these conditions are met. But as long as that condition is met, every time I'm actually verifying that L sub I is not equal to x, right? So if it becomes the case that I is equal to n at the end of this process, then most certainly it had to have been that every single time to finish this loop, it had to have been the case that every time it said it checked this. But that's each position in the array. Okay, question about, so what did you mean by I would be unbounded? So that's for the finite, the proof about terminating in finite time. So in that case, what I was saying is suppose that so if the while loop performed in, so I'm just simply observing that if I were unbounded, which it isn't, it's just a matter of argument. So if I were to tell you that I would be unbounded, that would mean that the loop would never terminate, right? Unless it got a match. But there's some cases where you're not going to be able to terminate if that were the case. But most certainly the big thing here is just that I'm just making a simple argument. You could have easily just switched my argument over here, which is saying, hey, look, every single time it increases I by 1, but notice that I is less than n. Hence, at some point, it will have to grow with some bound until it gets to n, which means that it has to finish. Okay, so how do we claim the second property? Yeah, no worries, no worries. Yeah, it was just one way of saying the same thing that I just said now. Wonderful. We say that the algorithm produces correct output. I will have the full proof in the notes. So please take a look at that after class. I just have to kind of walk past it a little bit because it takes a while for me to write it out. But it's not that long. It's actually just a paragraph or two. It's just a couple of paragraphs. One's a really short paragraph. The other one's just a paragraph. But it's just for these two cases here. One paragraph for one paragraph for the other. Remember, you just have two cases. So this is one common design way of, one common way of designing an algorithm is try to get it so that you could say, okay, either it does this or it does that. But yeah, no, does everybody get the general idea here of why linear search would always produce correct output though? Okay, good. Wonderful. You're going to find sometimes in this class, I'm going to just describe the idea for you. Sometimes I'm going to write it out for you. So I want to make sure you see both examples of this so that you can get an idea of like, okay, well, how can you argue to somebody that this works? It's very important that you see kind of both. But yeah, in the notes, I will have this proof, the one for the correct output. I advise you look at that. It'll be very helpful for the assignment probably. But yeah, the idea, remember, all I'm doing is just communicating an argument to you. So I want to switch gears now because we talked about correctness. Now, I want to talk a little bit about complexity now with the remainder of our time. So you may have talked a little bit about complexity before, but I most certainly am going to pin this down quite more carefully than you may have seen in the past. So I will tell you up front, if you've seen big O notation, you're going to see it again. And I'm going to talk a lot about big O notation in this course. So question, so we have to prove both properties. So yes, you have to make sure you know for every instance of the problem that your algorithm terminates in finite time, meaning that always will spit out output for you. It doesn't get stuck in an infinite loop. And the other condition is just to make sure that, yeah, your output is always correct. Wonderful. So I want to switch gears, talk a little bit about something that, because at some point I gotta get I go deep and then I come back up a little bit. This is going to be one of those cases. We're just going to talk a little bit about complexity analysis for the remainder of our day here today. We'll pick up more about this next class. So I want to talk a little bit about algorithms because, like, sure, we talked about algorithms over there. We talked about some formal stuff. I'm going to talk about more formal stuff, but I also have to keep in mind that I want to kind of give you a big picture look at a lot of this stuff. And I'm hoping in the next couple of lectures I'm going to motivate why maybe, I'm not sure if you've seen it in 115, most certainly you may have. Why you've seen big O notation, why do we use big O notation? Why is it useful for us? I'm going to try to address all these questions for you. So if you've seen it before, don't worry. We're going to talk all about that and how we use it for analyzing algorithms. So, which is going to be an important piece for when we start talking about data structures and algorithms in different settings. Because I would like some way to analyze an algorithm regardless of what the computer looks like, or what the programming language is, or things like that. So I have a question for you. This is just something. So what are desirable characteristics for algorithms so we can compare them? So I have a question for you. This is more of us trying to do a brainstorm here. So what are some desirable characteristics for algorithms? So if I want to take two algorithms and I want to compare them, what are some desirable characteristics that algorithms can have? So I see one, time to run. That's a lovely one. I'll include that. I'll write it as running time. Any other suggestions? There's plenty of things that you can compare algorithms by in different ways. Most certainly efficiency. I'll put that on. Now, there's several ways we can talk about efficiency. One is running time. Another one I will bring up here is space. So for example, space or memory usage. That's another thing we can always talk about. I've seen about complexity. We will talk about what I mean by this. So input, output. So so I like that suggestion. I really like that suggestion. Compiling time. These are lovely suggestions. I'm going to throw them under another bucket because I think that one thing that at least one idea. There's two things I can try to throw this under. So compilation time possibly might get thrown into this. Difficulty to implement, for example, that's something that we have to take into account. If you have a really complicated algorithm, you might have to spend a lot of time trying to teach people how this works. Other ones, if it's a very simple algorithm, it's simplicity. That may take a lot less time. But if it's difficult to implement, it may be a very sophisticated program that may take a long time to compile. Who knows? I've seen about complexity. I've seen readability. So I'll throw that under another bucket. I'll call simplicity. So I mentioned this. So for example, maybe one thing that would be nice is that maybe one algorithm is really complicated but really fast. But it's really hard to understand it and why it works. Then you have a really dead simple algorithm. Maybe it's a little slower, but most certainly it's easy to communicate to people. So from a communication standpoint, you might say, okay, well, if I have this really fast algorithm, it would be nice to be able to implement this. But at the same time, it only takes me like 5 seconds to explain this other algorithm to somebody. You'd see that maybe as a benefit, conceptually speaking, right? So some algorithms are very much like that, where somebody like me, I have to sit here explaining it for a solid lecture or two. Some really sophisticated algorithms can be like that. In fact, I can tell you that I've seen papers where the algorithm's description usually spoils out of a bunch of theory that's like 30 or 40 pages long. It's something that does happen. But yeah, no. Yeah, linear search, binary search, maybe that could be an example. Somebody was suggesting that. Yeah, binary search is a little bit more conceptually more complicated, but it is more efficient. Yeah, I think that's a pretty good example. yeah, so let's see. We got, running time, space usage. Here's another one. I seen it maybe mentioned in the chat about inputs or parameters. Another one that maybe is another one to maybe talk about is difficulty to modify or augment. So just as an example of this, when we talked about linear search, you notice that I made some assumptions about our set S, right? I told you it's an array. Now, conceptually speaking, linear search, if I made the set represented by something else, like a linked list, for example, now I wouldn't recommend doing that, but you most certainly could. You could walk through the whole process of scanning from left to right, except in that case, you would traverse the linked list, right? Linear search is a very simple algorithm that's very easy to modify for a different problem specification, right? And just as another example, and I think I see it in the chat actually. So I'll address that in one moment. That's a wonderful suggestion about longevity of software. So one thing that also to keep in mind is when you design software, oftentimes you have it where you design, but also you have to take into account that your software evolves over time. So there may be cases where you're considering only a very specific problem. And then maybe like a year later or 2 years later, or maybe 5 years later, who knows, some legacy piece of code. What happens is somebody comes along and says, hey, look, I need your algorithm in our C++ source code to also do blank. Can it do that? That is something that most certainly can happen. And that's actually one feature of an algorithm that'd be wonderful, is its ability to be modified or augmented so you can solve more problems. So oftentimes when I talk about an algorithm like linear search, I talk about the search problem, right? But I'm sure you've seen linear search been used in several other different kind of circumstances, right? Where you can traverse through all the elements and you scan them just to see if there's an element there or not. Most certainly you can use that just to simply traverse through the elements, just naturally. You can use that in a lot of different settings. But yeah, no, so I thought these would be some interesting things to brainstorm. But yeah, no, definitely there's a cost-benefit thing when involving all of these, right? Like all of these involve costs and benefits or trade-offs. So that's one thing that I really want you to emphasize with you, is that sometimes you're going to run into an algorithm where it's very efficient, but it may use more space. Sometimes you're going to run into algorithms where it uses very little space and actually is quite fast. Sometimes you're going to run into it where it uses very little space, but it runs really slow. Sometimes you're going to have algorithms where it's very simple, but it may actually be quite a bit slower than, say, another more contemporary algorithm is. But hopefully you're getting the idea, is that we want some way to compare algorithms. And that brings me to talking about complexity, okay? So I'm going to define a few things, then we're going to stop for today, okay? Because I want to make sure I give you back your time from the other day. So let me define a few things, then we're going to stop, and then we'll come back to it next time. Okay. So at first I need to define a useful definition for complexity, because you may have heard of this term, but what is complexity? So let me write out what I mean by complexity. So what I mean by complexity is the amount of resources, the amount of resources an algorithm uses. So that's what I mean by complexity. So if somebody talks about complexity, they're talking about the resources of the algorithm. Now there's another context for which we can talk about this, is about a given problem and asking how efficiently we can solve a problem. So for example, you may talk about the complexity in that context. In this course, we'll mostly focus on it from more of this approach, just talking about with respect to just algorithms and comparing two algorithms or three. So we're going to be interested in two kinds of resources in this class. And it was actually, both of them are on our list. We are interested in two computer resources. So the first one we're going to be interested in is space complexity. So this is the one that we'll focus not maybe as much on in this class, but most certainly it will come up very often when we talk about data structures and different kinds of implementations for certain kinds of data structures. Sometimes you'll find that you end up using a whole bunch of extra space that you don't need. Sometimes from algorithms, that'll be indeed the case. So this is just simply the amount of memory the algorithm needs. So for us, we're going to look at what we call extra or auxiliary space. So this would be where I give you the input, and all I want to know is how much the algorithm uses once given the input, how much it takes up and uses on your memory, as opposed to just the input plus this, which classically that's how you define space complexity. So you'll see this difference when we start talking about this. The other one is talking about time complexity. This is the one that we're going to focus a lot on in this class. So the amount of time needed by the algorithm to complete. So these are going to be our two primary measurements of things when we look at analyze and compare algorithms in this course, is these two. These are very commonly studied by computer scientists to study all sorts of fun problems. And we'd like to know in what circumstances can we come up with the most efficient algorithm with respect to how long it takes or even how much memory we use. You'll find that this measurement tends to be the most important because I'll give you a little rule. Very often when you run into issues with space, you could reuse space. You can't reuse time. Anyways, with that being said, when we come back, we'll talk more about complexity analysis and we'll do some examples. And that being said, I want to wish you a beautiful evening and I'll see you on Thursday, okay?